What would happen if you stepped into space right now? Would your body freeze instantly, skin turning rigid, breath crystallizing in a single moment? That is the image most people carry, a silent, instant death by cold. It feels obvious. After all, the universe around us sits at an average temperature of about 2.7 Kelvin, only a few degrees above absolute zero, so space must be unimaginably cold. End of story. But this answer, though intuitive, is fundamentally wrong. Because space is not cold in the way we understand cold. On Earth, cold is never experienced in isolation. It comes with air, with wind, with matter constantly pressing against your skin. Trillions of molecules collide with your body every second, carrying heat away. The faster this transfer, the colder you feel. Cold, in practical terms, is not something that surrounds you. It is something that happens to you. Now, remove the air. Remove every molecule that could touch your skin, every particle that could carry heat away through contact. What remains is not an extreme version of winter. It is something far more unusual. In space, there is almost no matter. A cubic centimetre of air on Earth contains roughly 10 to the 25th power molecules. In interstellar space, that same volume may contain 1 atom, or less. In many regions, it is closer to emptiness than to anything we would call an environment. This changes everything. Because without matter, the primary mechanism by which your body loses heat, direct contact, largely disappears. There is no icy wind, no surrounding medium pulling energy from you in the familiar way. So space does not feel cold because it is filled with cold substance. It feels extreme because it is almost entirely empty. This is the central misconception. We imagine space as a colder Earth. In reality, it behaves nothing like Earth at all. It does not actively cool you in the way air or water does. Instead, it simply removes the conditions that make temperature meaningful in everyday life. To understand this properly, we must separate two ideas we often merge without thinking: temperature and interaction. Temperature is not just a number assigned to a location. It is a measure of how particles move and exchange energy. Without particles, without collisions, the concept itself becomes difficult to apply in any conventional sense. Even the famous 2.7 Kelvin value does not mean that space is filled with cold matter. It reflects a faint background radiation, a residual energy field left over from the early universe, not a substance pressing against your body. So, when we say space is cold, we are compressing a complex physical reality into a familiar but misleading phrase. To understand how cold space truly is, and why that question is more complicated than it appears, we must first unlearn what cold even means. But this leads us to a deeper and more precise question. If space itself is not truly cold in the way we imagine, then why do planets far from the sun freeze so intensely? Why does the moon swing between extreme heat and extreme cold? And more importantly, if temperature depends on interaction, what exactly is being measured when we say something is cold at all? To answer that, we need to step back and examine temperature itself, not as a feeling, but as a physical quantity. That is where the next part begins. Temperature feels like a sensation. Something is hot, something is cold. But in physics, temperature is not a feeling, it is motion. More specifically, it is a measure of how fast particles are moving and how they exchange energy when they collide. A simple example helps clarify this. Imagine a room filled with air. Each molecule is in constant motion, moving in random directions, colliding with other molecules and with your skin. These collisions transfer energy. If the particles are moving quickly, they carry more energy, and we describe the system as having a higher temperature. On Earth, this process happens at an immense scale. In just 1 cubic centimetre of air, there are roughly 10 to the 25th power molecules. That is a number so large that collisions are not occasional events. They are continuous and unavoidable. Every moment your body is interacting with its surroundings through these microscopic impacts. This constant interaction is what gives temperature its practical meaning. Now consider the same volume in interstellar space. Instead of 10 to the 25th power molecules, you may find a single atom. In many regions, even less. The density drops so dramatically that collisions become extremely rare. Minutes, hours, or even longer may pass without a single interaction. At this point, the concept of temperature begins to lose clarity. Because if temperature depends on particles exchanging energy, what happens when those exchanges almost never occur? A useful teaching insight is this: temperature is not a property of emptiness. It is a property of systems where interactions are frequent enough to define an average behavior. This leads to a subtle but important conclusion. If you place a thermometer in space, it does not measure space itself. It measures its own internal state, how its particles are moving, how it gains or loses energy through radiation. In other words, the reading belongs to the object, not to the void around it. This distinction is essential because it tells us that temperature, as we commonly use the term, cannot be assigned to empty space in the same way it is assigned to air, water, or solid objects. So, when we say that space has a temperature, we are already simplifying a much more complex situation. To fully understand how objects gain or lose energy in such an environment, we must examine the fundamental ways heat can move. But this raises a more precise and unavoidable question. If temperature depends on interaction, and interaction in space is almost absent, then how does heat actually move at all in a vacuum? How does any object gain or lose energy when there is nothing to touch it, nothing to flow around it? There must be a mechanism that still works even in complete emptiness. What is it? If space is almost empty, then how does the sun still burn your skin from 150 million kilometers away? If heat cannot move through contact, and there is no medium to flow around an object, then only one mechanism remains. To see this clearly, we must examine how heat moves in general. There are three fundamental ways energy transfers from one place to another: conduction, convection, and radiation. Conduction is the simplest to visualize. It requires direct contact. When you touch a hot surface, energy flows from the faster moving particles in that surface into the slower moving particles in your skin. The transfer happens through collisions, one particle passing energy to the next. Convection works differently, but it still depends on matter. Here, entire regions of fluid move. Warm air rises, cool air sinks, creating circulation. This is how heat spreads through the atmosphere and oceans. It is not just particles colliding, but bulk motion carrying energy across space. Both of these mechanisms share a requirement: a medium. Without particles, neither conduction nor convection can occur. This is why, in the environment we have been describing, these two processes simply disappear. There is nothing to conduct through, nothing to circulate. So we are left with the third mechanism: radiation. Radiation does not require matter. Every object with temperature emits energy in the form of electromagnetic waves. These waves do not need particles to carry them. They travel through empty space freely, at the speed of light. A useful way to think about this is to consider sunlight. The sun is approximately 150 million kilometers away from Earth, separated by near-perfect vacuum, yet its energy reaches us continuously. It warms the ground, drives weather, and sustains life, all without any physical contact. This is radiation in action. In space, radiation is not just one method among several. It is the only method that remains effective over distance. This leads to an important consequence. An object in space does not lose heat because something around it is pulling that heat away through contact. Instead, it loses energy by emitting radiation outward in all directions. At the same time, it may gain energy if it absorbs radiation coming from other sources, such as a nearby star. Temperature, in this context, becomes a balance. Not a balance of collisions, but a balance of incoming and outgoing radiation. A surface facing a star receives energy and warms. A surface facing empty space loses energy and cools. The difference can be extreme, even across a single object. This is why the behavior of temperature in space often appears contradictory. It is not governed by surrounding conditions in the usual sense. It is governed by exposure. To understand just how dramatic this effect can be, we must look at what happens when a human-made object enters orbit and experiences both intense radiation and complete darkness. Why does an astronaut burn in sunlight and freeze in shadow at the same time? To answer this, consider a human body in orbit. An astronaut circling Earth is not surrounded by cold air. There is no atmosphere pressing against the suit, no medium distributing heat evenly. Instead, the astronaut is exposed directly to radiation, both incoming and outgoing. On the side facing the sun, energy arrives continuously. Solar radiation carries immense power, even across the vast distance of space. Without air to scatter or soften it, this energy strikes directly. Surfaces exposed to sunlight can reach temperatures above 120 degrees Celsius. Now consider the opposite side. Turn away from the sun, and the incoming energy disappears almost completely. There is no warm air to compensate, no surrounding environment to maintain balance. The object continues to emit radiation, losing energy into empty space. Temperatures can drop below minus 170 degrees Celsius. This creates a striking contrast. Across the same body, within a short distance, there can exist a temperature difference approaching 300 degrees. A useful teaching insight is this: space does not impose a temperature, it allows temperatures to diverge. On Earth, such extremes are rare because the atmosphere redistributes energy. Air moves, heat flows, and differences are smoothed out. In space, that smoothing mechanism is absent. Each surface behaves independently, responding only to the radiation it receives and emits. This is why the situation appears paradoxical at first glance. We expect an environment to define temperature, but in space, the environment does not regulate, it does not stabilize, it does not act at all. Instead, temperature becomes a local property, determined entirely by exposure. An object in sunlight heats up. The same object in shadow cools rapidly. The transition between these states can be abrupt, with no gradual buffering in between. Even spacecraft must be carefully designed to manage this effect. Surfaces are engineered to reflect, absorb, or emit radiation in controlled ways. Without such control, internal systems would quickly fail under these extreme and uneven conditions. So, the key idea is not that space is hot or cold. It is that space is indifferent. It neither gives nor takes energy on its own. It simply allows energy to arrive from sources like stars, or to leave objects into the vast emptiness. To see this principle more clearly, we can look at a natural example, one that experiences these extremes continuously without any protection. That example is the Moon, and it reveals the behavior of temperature in space with remarkable clarity. The clearest demonstration of everything we have discussed is not found in theory, but in a place we can observe directly: the Moon. At first glance, it appears calm and unchanging, but in terms of temperature, it is one of the most extreme environments in the solar system. During the lunar day, when the surface faces the sun, temperatures can rise to about 127 degrees Celsius. This is hotter than boiling water. The ground absorbs solar radiation continuously, with no atmosphere to reflect or distribute that energy. Now consider the lunar night. As the Moon rotates away from the sun, that incoming energy disappears entirely. There is no air to retain heat, no circulation to redistribute it across the surface. The same ground that was intensely hot begins to lose energy by radiation into open space. Temperatures fall dramatically, reaching approximately minus 173 degrees Celsius. This creates a temperature swing of nearly 300 degrees on the same surface. A useful teaching insight here is this: the Moon is not becoming cold because space is cold. It is becoming cold because it is losing energy without any mechanism to retain or redistribute it. On Earth, this kind of extreme variation does not occur. The atmosphere acts as a regulator. Air absorbs heat, moves it across regions and releases it gradually. Oceans store thermal energy and release it slowly. Even at night, the surface does not cool instantly because energy is shared across the system. The Moon has no such system. No air, no oceans, no weather, no buffering. Each location on its surface responds only to its exposure to radiation. When sunlight is present, it heats. When it is absent, it cools rapidly. There is no intermediate process to smooth the transition. This makes the Moon a natural experiment. It shows us, in its simplest form, how temperature behaves when matter is removed from the equation. What we observe is not the temperature of space itself, but the thermal response of an object interacting only through radiation. And this leads to an important clarification. The extreme cold of the lunar night does not come from space surrounding it. It comes from the surface losing energy until it approaches a deeper limit, a limit that exists everywhere in the universe. What determines that limit and why objects cannot cool indefinitely is the next question we must address. The Moon showed us that objects in space can cool dramatically, but it also points to a deeper limit. Cooling does not continue forever. If an object is placed far away from stars, far from any significant source of radiation, it will continue to lose energy over time. It emits radiation outward, steadily reducing its internal energy. But this process does not lead to absolute zero. Instead, it approaches a boundary. That boundary is approximately 2.7 Kelvin. To understand why, we must introduce a subtle but important presence in the universe. Even in the emptiest regions of space, there is still a faint background of radiation. It is extremely weak, but it exists everywhere, in every direction. This radiation is known as the cosmic microwave background. A useful way to think about it is as a thermal floor. No matter how much energy an object loses, it is still immersed in this faint glow. As it cools, it eventually reaches a point where the energy it emits is balanced by the energy it absorbs from this background radiation. At that point, cooling effectively stops. This creates a universal baseline temperature. An object cannot naturally cool below this value because it is always receiving at least a small amount of energy from its surroundings, even in what we consider empty space. This is why absolute zero, the point where all motion ceases, is never reached in natural conditions. There is always some residual energy, however small. A teaching insight here is that emptiness is not truly empty. Even the most isolated regions of the universe contain this faint radiation field. It does not feel like an environment in the traditional sense, but it still sets limits on how systems behave. So, when we say that the universe has a temperature of about 2.7 Kelvin, we are not describing a cold substance filling space. We are describing this background radiation that defines the lowest equilibrium temperature for objects. This reframes the idea of cosmic cold. The universe is not actively cold. It simply contains a minimal level of energy that nothing can naturally fall below. And this raises a natural question. Where did this background radiation come from? Why does it exist everywhere? And why does it have precisely this temperature? To answer that, we must go back to the origin of the universe itself. The limit we have reached, this faint 2.7 Kelvin background, is not an accident of nature. It is a remnant. To understand it, we must shift our perspective from space as it is now to the universe as it once was. In its earliest moments, the universe was not cold, empty, or quiet. It was dense, extremely hot, and filled with energy. Temperatures were not measured in degrees above zero, but in thousands, even millions of degrees. Matter and radiation were tightly coupled, constantly interacting, exchanging energy in every direction. A useful way to think about this is to imagine a glowing furnace, where energy is so intense that nothing can exist without being affected by it. In that early universe, light could not travel freely. It was scattered continuously by charged particles, trapped in a dense, opaque environment. But the universe did not remain in that state. It expanded. As space itself stretched, the energy within it spread out. With expansion came cooling. Temperatures dropped gradually, allowing particles to slow down and combine. Electrons joined with nuclei to form neutral atoms, reducing the constant scattering of radiation. This moment, often called recombination, changed everything. For the first time, radiation was able to travel freely across the universe. What had once been trapped light became a vast, expanding field of energy, moving in all directions. Over billions of years, as the universe continued to expand, that radiation stretched as well. Its wavelengths grew longer, its energy diminished, and its temperature fell. What remains today is not the intense heat of the early universe, but its cooled residue, a faint glow, uniform, persistent, and present everywhere. This is the cosmic microwave background. A teaching insight here is that we are not just observing empty space when we measure this radiation. We are observing a historical signal, a direct imprint of the universe's early conditions. It is in a very real sense a thermal memory. Every direction we look, this radiation appears nearly identical. This uniformity tells us something profound. The early universe itself was remarkably consistent in temperature across vast distances. So the 2.7 Kelvin limit we observe today is not simply a boundary imposed by physics in isolation. It is the cooled echo of a once extremely hot universe, stretched and diluted over 13.8 billion years of expansion. Cold, in this context, is not the absence of history, it is the result of it. And this raises an important question. If this faint radiation fills all of space, how did we first detect it? How did we confirm that this quiet signal truly exists everywhere, carrying the imprint of the universe's origin? How did scientists accidentally hear the universe itself? The prediction of a faint, uniform radiation filling the universe was not initially a direct observation. It was a theoretical consequence of an expanding, cooling cosmos. The challenge was to detect it. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working with a sensitive microwave antenna. Their goal was not to study the origin of the universe. They were calibrating their instrument for communication experiments. Yet, a persistent signal remained. It appeared as a low-level noise, uniform in every direction. Day or night, summer or winter, the signal did not change. It did not depend on where the antenna pointed. At first, they treated it as an experimental problem. They checked for technical faults. They accounted for known sources of interference. Even contamination inside the antenna was removed in an attempt to eliminate the signal. Nothing worked. The noise remained. A useful teaching insight here is that discovery in science often begins as confusion. When an observation refuses to disappear, it demands explanation. At the same time, other researchers had predicted that if the early universe had once been hot and dense, there should still be a residual radiation present today, cooled and shifted into the microwave range. When the two results were compared, the conclusion became clear. The noise was not noise, it was the universe itself. What Penzias and Wilson had detected was the cosmic microwave background, the very radiation we described earlier. It arrived uniformly from all directions, confirming that this was not a local phenomenon, but a property of the entire universe. Later missions refined this measurement with increasing precision. Satellites such as COBE, WMAP, and Planck mapped this radiation in detail, confirming its temperature at approximately 2.725 Kelvin. Even more remarkably, the spectrum of this radiation matches almost perfectly with that of an ideal blackbody, an object that absorbs and emits energy in the most efficient way possible. This level of precision is not accidental. It reflects the conditions of the early universe, when matter and radiation were in near-perfect equilibrium. So what began as an unexplained signal became one of the strongest pieces of evidence for our modern understanding of cosmology. We are not simply measuring a temperature. We are observing a relic, a direct connection to a time when the universe itself was a hot, dense system. And this leads to a broader perspective. If such extreme heat once existed everywhere, then the cold we observe today must be the result of transformation over time. Understanding that contrast between rare regions of intense heat and the vast background of cold is essential to grasping the true nature of the universe. If the universe began in extreme heat, then why does it now appear overwhelmingly cold? To answer this, we must look not at isolated objects, but at scale. The cosmos, when observed as a whole, is not a uniform environment. It is a structure of contrasts. Regions of intense energy exist, but they are rare and highly localized. Stars, for example, operate at extraordinary temperatures. The core of a typical star reaches millions of degrees, sustained by nuclear fusion. In more extreme events, such as supernova explosions, temperatures can rise to tens of billions of degrees. These are among the most energetic processes in the universe. Yet these regions occupy a very small fraction of space. A useful teaching insight here is to think in terms of proportion. Imagine a vast ocean with a few scattered sparks. The sparks are bright, intense, and energetic, but they do not define the overall state of the ocean. In the same way, stars and galaxies are concentrated pockets of heat within an otherwise sparse and expanding universe. Even entire galaxies containing billions of stars, occupy a negligible fraction of cosmic volume. The distances between them are immense. Between these structures lie vast regions with almost no matter and minimal radiation beyond the faint cosmic background. This leads to an important conclusion. Heat exists, but it is not widespread. Most of the universe resides in conditions close to the baseline temperature of approximately 2.7 Kelvin. These regions are not actively cooled by an external force, they simply lack sources of energy. So while extreme heat can and does occur, it is statistically rare when considered across the entire universe. This reframes how we should think about cosmic temperature. We do not live in a universe where hot and cold are evenly distributed. Instead, we live in a universe where small, dense regions generate immense heat, while the vast majority of space remains near its minimal energy state. This imbalance is not temporary. It is a direct consequence of expansion, distribution of matter, and the way energy is produced and dispersed. So, the question is no longer whether the universe contains heat. It clearly does. The more important question is this. When we consider the universe as a whole, what dominates its overall condition? To answer that, we must step back even further and consider where a randomly chosen point in the universe would most likely place us. What would you actually see if you were dropped somewhere random in the universe? Not a star, not a planet, not even a galaxy. You would find emptiness. To understand this, we must think in terms of probability, not familiarity. Our experience is shaped by being inside a dense region of matter. We see stars, planets, and galaxies, and we assume these define the universe. They do not. They are the exception. The large-scale structure of the universe is dominated by vast regions known as cosmic voids. These voids contain extremely little matter, no stars, no significant radiation sources, and almost no interactions of any kind. Estimates suggest that these voids occupy roughly 80 to 90% of the total volume of the universe. A useful teaching insight here is to separate presence from dominance. Stars are bright and energetic, but they occupy a negligible fraction of space. Their influence is local, their visibility is high, but their volume is small. In contrast, emptiness is not visible, but it is dominant. So when we ask what the universe is mostly like, we are not asking about what is most noticeable. We are asking about what is most common. And what is most common is a near-perfect vacuum, filled only with the faint cosmic microwave background radiation at approximately 2.7 Kelvin. This leads to a clear and unavoidable conclusion. The universe is not a place where heat and cold compete on equal terms. Heat exists, but it is confined. It appears in small, dense regions where matter has accumulated and energy is actively produced. Cold, by contrast, is everywhere else. Not as a force, not as a substance, but as the natural state of a universe that is expanding, thinning, and distributing its energy over ever-increasing distances. So, when we describe the universe as cold, we are not describing a condition imposed from outside. We are describing the statistical reality of where most of space exists. A final way to frame this is simple. If you could choose any location at random, you would almost certainly find yourself in darkness, surrounded by near emptiness, with only the faint afterglow of the universe's origin remaining. Cold has not defeated heat through competition, it has prevailed through scale, and that is why, when viewed as a whole, the universe is defined not by its brightest regions, but by its vast and quiet emptiness.